The field of astrophysics is rife with mysteries, but none more perplexing than black holes. These cosmic oddities, first posited by Einstein's theory of general relativity in 1915, challenge our very understanding of physics, space, and time. They are regions of space where gravity is so strong that nothing, not even light, can escape from them, earning them their black moniker.
It is the human version of the Roach Motel. You check in, but you don't check out. A black hole. That's why we call them black. And when you fall in, you don't come out, that's why we call it a hole. Because we tell it like it is in astrophysics.
Over the past few years, spectacular observations using gravitational wave detectors and vast telescope arrays have given us a deep look at the mysterious black holes, exposing their formation, characteristics, and role in the cosmos. But the big mystery still remains. We don't know what lies at the center of a black hole, beyond the boundary where matter winks out of view forever. But now, in an extraordinary claim, famous astrophysicist Neil deGrasse Tyson just revealed, quote, "We finally know what's inside black holes," end quote. Join us today as we embark on an awe-inspiring journey through the hidden universe of black holes, unlocking the unimagined secrets of what's inside the gluttonous monsters. So, without any delay, let's get started. In 1967, the physicist John Wheeler was giving a lecture about a mysterious and startling phenomenon in deep space that the field was just beginning to understand. But it didn't have a great name to match. Wheeler and his audience were equally tired of hearing gravitationally completely collapsed object over and over, so someone threw out an idea for a different name. A few weeks later, at another conference, Wheeler debuted the suggestion, black hole. And it's perfect, isn't it? What else would you call a dark abyss that swallows light and matter and doesn't let go? Decades later, black holes, invisible, impenetrable, and many light years away, are more familiar to us than ever before.
Black hole is a region of space where matter has condensed to such a high density that the gravity at its surface, the surface gravity, is so high that you cannot escape it, even at the speed of light. You are forever trapped. It is the fabric of the space-time continuum warped back on itself. And once you fall in, you are never coming out.
There are 4 types of black holes: stellar, intermediate, supermassive, and miniature. The most commonly known way a black hole forms is by stellar death. As stars reach the ends of their lives, most will inflate, lose mass, and then cool to form white dwarfs. But the largest of these fiery bodies, those at least 10 to 20 times as massive as our own Sun, are destined to become either superdense neutron stars or so-called stellar mass black holes. In their final stages, enormous stars go out with a bang in massive explosions known as supernova. Such a burst flings star matter out into space, but leaves behind the stellar core. While the star was alive, nuclear fusion created a constant outward push that balanced the inward pull of gravity from the star's own mass. In the stellar remnants of a supernova, however, there are no longer forces to oppose that gravity, so the star core begins to collapse in on itself. If its mass collapses into an indefinitely small point, a black hole is born. Packing all of that bulk, many times the mass of our own Sun, into such a tiny point gives black holes their powerful gravitational pull. Thousands of these stellar mass black holes may lurk within our own Milky Way galaxy. But there is one kind of black hole that is not like the others.
Gotcha.
This is dark, and it has huge mass, and it's small. That's 3 smoking guns right there.
Right.
Implicating a supermassive black hole.
Supermassive black holes, predicted by Einstein's general theory of relativity, can have masses equal to billions of suns. These cosmic monsters likely hide at the center of most galaxies.
We're just resigned to the fact that every
Right.
galaxy's got a black. Even some of the smaller galaxies that might not have, they got black holes.
They still
too.
have black holes, right?
So no, we haven't measured every one of the 100 billion galaxies in the universe, but every galaxy we measured, the big ones, the small ones,
Right. It's like taking a poll.
yeah, except even better.
Right.
Because the universe doesn't.
The Milky Way hosts its own supermassive black hole at its center, known as Sagittarius A, with an asterisk after the A, pronounced A star, that is more than 4 million times as massive as our Sun. The tiniest members of the black hole family are, so far, theoretical. These small vortices of darkness may have swirled to life soon after the universe formed with the Big Bang some 13.7 billion years ago, and then quickly evaporated. Astronomers also suspect that a class of objects called intermediate mass black holes exist in the universe, although evidence for them is so far debatable. No matter their starting size, black holes can grow throughout their lives, slurping gas and dust from any objects that creep too close. Anything that passes the event horizon, the point at which escape becomes impossible, is in theory destined for spaghettification, thanks to a sharp increase in the strength of gravity as you fall into that black hole. Astrophysicist Neil deGrasse Tyson once described the process.
But if you happen to fall in a black hole, which is my preferred form of death, it's better than getting hit by a bus, right? So if you fall in a feet-first dive to this cosmic abyss, you will not survive because you will not miss.
But black holes aren't exactly cosmic vacuum cleaners, as often depicted in popular media. Objects must creep fairly close to one to lose this gravitational tug-of-war. For example, if our Sun was suddenly replaced by a black hole of singular mass, our planetary family would continue to orbit unperturbed, if much less warm and illuminated. But because black holes swallow all light, astronomers can't spot them directly like they do the many glittery cosmic objects in the sky. But there are a few keys that reveal a black hole's presence. For one, a black hole's intense gravity tugs on any surrounding objects. Astronomers use these erratic movements to infer the presence of the invisible monster that lurks nearby. Or objects can orbit a black hole, and astronomers can look for stars that seem to orbit nothing to detect a likely candidate. That's how astronomers eventually identified Sagittarius A star as a black hole in the early 2000s. Black holes are also messy eaters, which often betrays their locations. As they sip on surrounding stars, their massive gravitational and magnetic forces superheat the infalling gas and dust, causing it to emit radiation. Some of this glowing matter envelops the black hole in a whirling region called an accretion disk. Even the matter that starts falling into a black hole isn't necessarily there to stay. Black holes can sometimes eject infalling stardust in mighty radiation-laden burps. In 2019, we even got pictures that show a black hole as an imposing shadow against the glow of cosmic material.
We physicists have waited 100 years since 1916 for this photograph. This photograph is the smoking gun.
Scientists then have detected the gravitational ripples that result when black holes smash into each other. The entire cosmos, we recently learned, might be humming with the force of such collisions. The list goes on. But the big mystery still remains. We don't know what lies at the center of a black hole, beyond the boundary where matter winks out of view forever. As Elliot Quater, a theoretical astrophysicist at Princeton, said, "The question is definitely answerable in that someone could fall inside the black hole and find out the answer. The problem is, they couldn't convey that answer to someone outside the black hole because nothing can get out." Because such hands-on observation is impossible, scientists must approach the subject theoretically. The effort involves mind-bending physics calculations, endless thought experiments, and serious entertaining the possibility that the universe is delightfully weirder than we can imagine. It also requires accepting that we'll never really truly know for sure what's inside a black hole. For us Earthlings, a bottomless pit more massive than the Sun might be difficult to fathom. Black holes are not solid objects, like planets or asteroids, Shane Larson, a physics professor at Northwestern University, said. They're more like regions in space, seemingly empty spots made noticeable by the stars orbiting wildly around them. It's kind of like an open window, Larson said, an invisible line that separates exterior from interior. To understand why black holes scramble our understanding of cosmic forces, we need to think about their structure. If a black hole were a Ferrero Rocher chocolate ball, the first layer of chocolate and crushed hazelnuts would be the region just outside the event horizon, where gravity is still weak enough that a nearby star could safely whiz by and not fall in. Next up is a layer of crispy wafer. This is the event horizon, the point of no return. Under this layer lies smooth chocolate filling, through which trapped cosmic material is sucked toward the center. And then there's the heart of the Ferrero candy, the whole roasted hazelnut. This is the singularity, a tiny, concentrated point of infinite destiny. Physicists believe they understand what the space beyond the event horizon, nearly all the way through the chocolate filling, should look like, based on Einstein's theory of general relativity. If an astronaut were to fall into a black hole, she or he would descend, and as she or he went deeper, she would experience the very fabric of space-time warping all around her. The 1915 theory describes well what must occur in such an extreme environment, where gravity overwhelms all other forces in the universe. The trouble starts farther in, closer to the singularity, where the laws of physics as we currently understand them break down, Larson said. Deep inside a black hole, general relativity isn't enough to explain what's happening. You also need a different kind of physics, quantum mechanics, which deals with the tiniest particles of the universe, atoms, and their even smaller components. When collapsing all matter down to a point, as a black hole does, the size gets small enough that quantum effects become important, says James Miller Jones, an astronomer at Curtin University in Australia, who shared his thoughts in an email. Unfortunately, general relativity and quantum mechanics do not get along. According to the principles of general relativity, once stuff goes into a black hole, it's lost for good. You can determine some fundamental properties of the black hole, such as its mass, but not its constituent parts. In the 1970s, Stephen Hawking showed that black holes actually evaporate very slowly, emitting radiation from just outside the event horizon. This development should have been thrilling for quantum mechanics, which dictates that information can't be destroyed. If someone took apart a complete puzzle and scattered it around your garden, you could collect the pieces and put them together again, Nicholas Warner, a physics and astronomy professor at the University of Southern California, said. It would take some time, though, and effort without a picture to guide you. But quantum theory says you could do it. But the particles wafting off black holes seem entirely devoid of information about the contents of their interior, a clear-cut violation of that principle. It's as if someone had run all those puzzle pieces through a washing machine, and they all become this gloppy gray mess, Warner said. Theoretical physicists around the world are trying to reconcile this mismatch between general relativity and quantum mechanics. Warner is a member of the camp that believes that Einstein's theory, the very principle that predicted the existence of black holes before astronomers even found evidence of them, is incomplete. Other experts feel the same, but say Einstein isn't the only one to blame. Maybe you have to change quantum mechanics too, Daniel Harlow, a physicist at MIT, told us. Harlow and his colleagues have posited that the radiation that Hawking discovered is indeed encoded with information from the depths, and our understanding of quantum mechanics isn't good enough yet to unscramble it. Everyone is searching for a theory of quantum gravity that avoids any contradiction. We don't have one of those, Charles Haley, an astrophysicist at Columbia University, said to us. Not even close, he said. But some physicists said the field could crack it within decades, certainly in this century. Scientists would finally know then, but only in a theoretical sense, of course. That's the thing about black holes. We can get only so close to the truth, only experience certain kinds of knowing. Even the powerful telescopes that have shown us sparkling galaxies nearly all the way back to the Big Bang can't help us here. Observationally, we're almost certainly not going to learn anything about the inside of a black hole in this century, Carl Rodriguez, a physics professor at the University of North Carolina at Chapel Hill, told us in an email. The best thing we can do is to study some effects of black holes. Maya Fischbach, an astrophysicist at the University of Toronto, thinks we'll learn more by studying the invisible gravitational waves that fan out when two black holes collide and merge into one. Those waves carry with them information about the newly formed black hole, which vibrates in the aftermath of its creation like a bell. Just like listening to a ringing bell can tell us what the bell is made of, listening to the black hole ringing can tell us what the black hole is made of, Fischbach said to us. But the purest form of discovery will always remain out of reach. If know means a student could take a field trip, observe directly with their own senses, then come back and write a class report about what they observed, then we will never know what's inside, Larson said. Perhaps that's not the worst thing. If it were easy to encounter situations like that, environments with extreme drag-you-into-the-abyss gravity, it would probably be bad for us, Harlow said. Safer to study black holes from afar, in our quiet cosmic neighborhood where gravity is far weaker and we can overcome it each day, simply by pulling back the covers and getting out of bed in the morning. Regardless, the gluttonous beast has always captivated our imagination. They are shrouded in mystery and hold mind-blowing secrets that continue to intrigue scientists and space enthusiasts like us alike. And in a shocking revelation, these astrophysicists speculated that these unusual black holes exist in the nearby universe, and that they could be untapped clues to the universe's infancy and adolescence. We can weirdly learn about the super beginning of the universe by looking at things really close to us, says theoretical astrophysicist Gillian Bellovary of Queensborough Community College in New York City. The notion remained just an idea for years, but now the existence of these misfits isn't so easy to ignore. Astronomers have turned up signs of a number of unexpectedly massive black holes in their universe's tiniest galaxies, and surprisingly, some of those black holes don't appear to sit at their galaxy's centers at all. Even more intriguing, astronomers have spotted evidence of black holes wandering at the galaxy edges, and in rare cases, being kicked from their homes into intergalactic space. Perhaps these black holes aren't merely cosmic nonconformists, but instead big players in the story of our universe. If so, they are a tool for probing one of the greatest mysteries in all of astrophysics, how the cosmic chamapas we see today came to be. Without understanding what black holes are doing, you cannot understand galaxy evolution, says Jiao-Hui Fan, a cosmologist at the University of Arizona in Tucson, making it impossible to explain the landscape of the universe. Our current cosmological understanding of how black holes got so big goes something like this. As galaxies grow, collide, and merge over cosmic time, they take on gobs of new stars, gas, and dust. The black holes at the galaxy's centers grow in lockstep, ballooning as they merge with one another and feed on the newly acquired material. A rough estimate puts a supermassive black hole's heft at somewhere around 1,000th of the mass of its home galaxy. In this scenario, the universe's littlest galaxies, called dwarf galaxies, probably didn't go through many mergers in the past. Tipping the scales at only about 1/millionth the mass of the Milky Way, they should have relatively runty black holes, or none at all. But in late 2000s, astrophysicist Marta Voluntari of the Institute of Astrophysics in Paris at Sorbonne University helped run computer simulations that track the evolution of massive black holes from birth to today. In those efforts, almost as soon as they popped into existence, even the smallest galaxies could have surprisingly large black holes. As time passed, some of those galaxies never grew or merged with others, leaving them unmarred after billions of years of cosmic evolution. A wild idea occurred to Voluntari and her colleagues. These galaxies and their black holes were relics of the universe's birth. If massive black holes and dwarf galaxies did exist, and if astronomers could find them, those black holes would be an unprecedented window into how the first black holes formed. The first hints that they do exist came from a serendipitous find by astronomer Amy Rines. More than a decade ago, she was in graduate school at the University of Virginia in Charlottesville, poring through telescope data on a dwarf galaxy 30 million light-years from Earth. It was bursting with stars, and Rines was trying to learn more about how these balls of hot gas are born. Initially, Rines looked at data from the galaxy called Hines's 2-10 in ratio and near-infrared wavelengths of light. She spotted a cosmic baby rattle, a roughly 300 light-year-long bridge of gas connecting two dusty balls swaddling newly coalescing stars. A deeper dive into the data revealed extreme radio emissions right in the middle of the rattle, along with bright X-rays coming from the same spot. Inklings of a huge black hole with a mass of 1,000,000 suns. "I hadn't seen this before," says Rines, now at Montana State University in Bozeman. Dwarf galaxies, she too had assumed, shouldn't have big black holes. She remained skeptical of her interpretation until a few months later, when she attended a talk in Seattle at the 2011 American Astronomical Society meeting. It was there that Bellovary, then a postdoctoral researcher at the University of Michigan in Ann Arbor, and collaborating with Voluntari, presented new simulations of galaxy formation. Bellovary described the formation of galaxies with a range of masses and histories, and discussed how the results could make predictions about how massive black holes are scattered throughout the universe. Like Voluntari's early work, Bellovary's simulations suggested that big galaxies were not the only ones to harbor big black holes. Scrawny galaxies could have them too. In a session at the same meeting, Rines highlighted her discovery of dwarf galaxy Hines's 2-10 and its uncharacteristically massive black hole, like two black holes circling each other and then colliding. Unexpected computer simulations met unexpected real-world observations. The combined work suggested that not only do massive galaxies have big black holes, but maybe a majority of galaxies do too, Fan says. And that raised a lot of new questions about how black holes and galaxies grow up together. After hearing Bellovary's talk and publishing her own findings, Rines has shifted her research focus from the birth of stars to finding big black holes. The behemoths pulled her in. She launched an effort to search for them in dwarf galaxies. Like other astronomers, she decided to scan the skies for the rings of cosmic crumbs that burn brightly around feeding black holes at the centers of galaxies, active galactic nuclei. That's where black holes should be, she assumed. I mean, it's in the name, active galactic nuclei, she explains. Rines combed through the data from the Sloan Digital Sky Survey, looking for the visible light signatures of central black holes. Of the roughly 25,000 dwarf galaxies in her analysis, 151 of them appeared to harbor a big black hole. She and her colleagues reported this in 2013. Voluntari says she was elated with the results. They validated her wild idea that dwarf galaxies could have really big black holes, and possibly that those black holes could tell us something about the very first black holes. A key clue may be in the masses of the dwarf galaxies' black holes. The two leading ideas for how the first black holes formed create black holes of different masses. One idea supposes that these black holes formed from the implosion of the first stars and would tend to be relatively lightweight. The other idea suggests that the first black holes formed from the direct collapse of giant gas clouds and would be heavier. If the gas cloud idea is correct, it could explain another cosmic puzzle: how black holes in the early universe got so big so fast. We observe them, and they are already huge, Bellaveri says. If the history of the universe was displayed on a clock, these monsters would have mere seconds to form, she explains. If big black holes in dwarf galaxies are indeed ancient relics from the early universe, their masses should be akin to the masses of the first black holes. If so, they could help explain how the seeds of some of the heftiest black holes we see today were formed. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, and subscribe if you haven't already, and hit that bell so you never miss out on future episodes. Be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this, and to always improve. And as always, thanks for watching, and we'll see you next time.